Okay, let's get started. I think I'll handle one question before we start the virtual memory lecture. It's related to prefetching. One fellow student asks, is prefetching also done between different cache layers, or would it make sense to apply different prefetching for different cache layers? Absolutely, yes. So you can customize the prefetching algorithm and the technique to the layers that the prefetching is targeting. Basically, if you have an L1 to L2, L2 to L1 prefetcher, for example, then you may want to employ a different algorithm than what you would employ from main memory to L4, let's say, for example, or main memory to the processor. So certainly, you may actually use different prefetching algorithms. In fact, in existing systems, there are different types of prefetching algorithms that are used because you can exploit the properties, locality properties, and the information that's available to different layers, of course, right? Because you have different levels of information, different levels of locality, both spatial and temporal, that is present at different layers, as we discussed when we talked about multi-layer hierarchies. So a very good question. Okay, now we're done with prefetching. Of course, I think this is a topic that you can immerse yourself endlessly with. And if you're interested, I would recommend looking into future lectures. Now let's move to virtual memory, another fundamental topic that's extremely important. Another idea that was developed in the 1960s. Prefetching was first developed in the 1960s also, actually, in IBM 360 systems, for example. Even earlier, actually, they developed next-line prefetchers for instructions. For example, in IBM 36091 had next-line prefetcher for instruction prefetchers. Basically, whenever you wanted one cache block, the system automatically prefetched the next cache block, for example. Virtual memory was also developed in the 1960s. And while prefetching has evolved a whole lot over the last 60 years, let's say, unfortunately, virtual memory has not evolved as much, I should say, compared to the 1960s. Of course, it has evolved a little bit, right? But not as much. And maybe it requires some rethinking today going into the future. And we will talk about that probably tomorrow if we have time. But one of the reasons why it has not evolved as much is because it's not a microarchitecture level mechanism that's invisible to the software. And prefetching can be, right? If you're doing it hardware level, run it is completely invisible to the software, for example. But virtual memory is not, as we will see. It's really a system level mechanism, and it's actually dictated by the ISA. And once ISA actually dictates a virtual memory system, it's hard to change it fundamentally, at least. You can keep extending it like what we've been doing and like what we will see in this lecture, but it's going to be very hard to change. And that's what we have been seeing in virtual memory systems, even though some of the things that we do in virtual memory are not as optimal and they cause a lot of overhead. We do it because we need to be backward compatible with the past versions of the ISA, especially x86, for example, but other ISAs have a similar problem with virtual memory today. Okay, okay, that was lecture break, unfortunately, but I should eliminate that slide. Let's eliminate it. Okay. So these are some readings. There, essentially, virtual memory is covered in H&H, Harris and Harris. I'd recommend going through it. I'm going to use some slides from them, but the reading that I recommend on memory systems that we have written is also recommended. And these are two readings that I recommend. This is a survey paper from 1998 that talks about some implementation issues in virtual memory. I think it's good to look at. And then this is a more recent paper that my research group wrote on rethinking virtual memory, such that maybe you can do a better thing than what you can overcome some of the shortcomings. But before we go into the shortcomings, we should really learn about what virtual memory is. And so far, this was the programmer's view of memory, right? The programmer basically can do loads and store to memory. And I've shown you this picture before, right? Actually, I've shown you this also before. Ideal memory, we want zero latency, infinite capacity, zero cost, infinite bandwidth. That sounds great. So far, we've talked about latency a lot, capacity a lot, cost a lot, bandwidth a lot, but we didn't really talk about the programmer's view of main memory as much. And virtual memory is going to be related to capacity, but from a programmer's perspective. And I actually showed you the slide earlier before we started going deeper into the physical memory subsystem, the caching subsystem, etc. I said that we're going to talk about physical addresses, physical memory, but programmer actually sees virtual memory. Now we're going to talk about what that is. Basically, virtual memory allows the programmer, the main memory size is infinite or large enough so that they don't need to worry about it. But in reality, physical memory size is much smaller than what the programmer assumes in many real systems today. That was not necessarily the case in the past. But the system in virtual memory, the system software and hardware cooperatively map virtual memory addresses to physical memory addresses in existing systems. And the system automatically manages the physical memory space transparently to the programmer, so that the programmer doesn't worry about running out of the main memory space. And that's one huge benefit of virtual memory, one of the reasons why it's there. The programmer should not worry about managing, worry about running out of physical memory and managing the data and code blocks such that you don't run out of physical memory, basically. The system transparently provides that support, both in hardware and software. So this is one of the most successful hardware-software cooperative design ideas that has permeated all our computing systems today, essentially. Almost all our computing systems today. Almost all computing systems have virtual memory. And even if they don't have today, 10 years from now, they may have virtual memory, because some accelerators may not have virtual memory. But as they become more general purpose over time, you will need this sort of support to make programmers' life easier. So basically, the big benefit, as we discussed earlier, is programmer does not need to know the physical size of memory, nor do they need to manage it. So a small physical memory can appear as a huge one to the programmer. As a result, life is easier for the programmer. Of course, every idea comes with a downside. Now you have a more complex system software and more complex architecture to do this automatic management for the programmer. And this is a classic example of the programmer architect, micro-architect trade-off, as we discussed. You try to make life easier for the programmer, but the hardware designer's life becomes harder. In this case, system designer's life becomes harder also to maintain this illusion that we're going to talk about. So we have already discussed the benefits of automatic management of memory between the caches, right? And you can imagine that this just extends to main memory as well. Basically, if you look at main memory, programmer now doesn't need to deal with physical addresses. And they don't need to deal with running out of space in the physical memory address space. That's the key benefit. And we'll talk more about that. And also at the same time, each process has its own independent mapping of virtual to physical addresses. Each process has a different virtual to physical translation mapping. As a result, the processes can be isolated from each other in physical memory. And the programmer doesn't need to worry about that sort of isolation also. So there are two benefits. One is the illusion of infinite memory, if you will, and the second is isolation between processes. But actually, I'm going to show you more benefits over here. So basically, having these properties enables code and data to be located anywhere in physical memory. So you can relocate the code and data at different places. You can flexibly locate data. For example, a huge array, a 1 gigabyte array does not need to be consecutive in memory. You can chunk, it does not need to be consecutively allocated in the physical memory space, right? You can chunk it into different pieces, and you can basically use available parts in the physical memory, as we will see. Isolation and separation of code and data of different processes in physical memory is enabled, as I mentioned, because each process has its own independent mapping of virtual to physical addresses. This leads to protection and isolation between different processes that are running concurrently in the system. So it enables multi-programming. One of the reasons why virtual memory was not present in very early systems is because those systems were not multi-programming systems. They were belonging to a single program. You were not executing other programs concurrently. But today, almost all systems are multi-programming systems. And if you want protection and isolation, virtual memory is one way of doing it. Code and data sharing between multiple processes also becomes easier. This is called sharing in general, because by just having a mapping mechanism, you can map different virtual addresses in different programs to the same physical address so that they can share data, for example. So this mapping mechanism between virtual and physical addresses enables multiple benefits, as you can see, and as we will see in a bit more detail. So let's take a look at a system with physical memory only. This is what we have assumed so far, basically. CPU, load and store instructions, generate physical memory addresses. This could be an accelerator also. It could be any computation unit. Whenever you're accessing memory, you're really accessing directly physical locations, right? So examples, early supercomputers, certainly most Cray supercomputers, early personal computers, many older embedded systems are like this. Many modern systems, except for accelerators, actually have virtual memory today. In fact, even GPUs are moving towards having more sophisticated virtual memories today, going into the future. So basically, why do we want it then? Basically, the problem is physical memory is of limited size because of cost, right, reasons, as we discussed. What if you need more? Should the programmer be concerned about the size of their code and data blocks fitting physical memory? What if the code and data doesn't fit physical memory? What does the programmer do? Does the programmer need to explicitly bring the data from the disk to the physical memory? In fact, that's what people used to do in the past when virtual memory automatic management was not present. This is called programming using overlays or overlay programming. They used to basically overlay while they're operating on some code inside physical memory or data inside physical memory, they would bring or prefetch, let's say, data from the disk into physical memory. And this is a lot of effort on the programmer's end, and it was a mess basically for average programmers in general. And that's what I said basically. Should the programmer manage data movement from disk to physical memory? Probably not the average programmer at least. On top of this, multiple programs may need the physical memory concurrently at the same time. Should the programmer make sure all processes, meaning different programs, can fit in physical memory? How do you even do that? Because the processes may not belong to a single programmer, right? The processes may belong to different people that are sharing the machine. And this is not an easy task. And this is also one of the reasons why early operating systems were developed to distinguish between different processes and schedule them, deschedule them, etc. And virtual memory was a synergistic idea to provide protection and isolation between these different processes. And then the next question is, and also enable the fitting of these different processes to physical memory. Should the programmer ensure two processes do not unintentionally or incorrectly use the same physical memory portion? Because you may be executing two processes. Clearly, the processes normally do not communicate, right? If you're operating on your array, if some other program should not be writing or reading your array, right? Clearly, that's a big security problem, and also a reliability, dependability problem, because if you're operating on some array and somebody else is modifying your data, even though they were not supposed to, then you have a protection and isolation problem. And it's very difficult for the programmer to ensure that without any system support. And virtual memory is one way of actually helping multiple programs execute at the same time, concurrently, or over time also. But concurrently is the harder problem, of course, right? And also, one other issue is ISA can have an address space greater than the physical memory size. For example, many ISAs today have a 64-bit address space with byte addressability, but clearly we don't have 2 to the 64 byte memories. That's huge, right? And what if you do not have enough physical memory? Then your 64-bit address should not be physical, right? Or you need to translate it in some way, which brings you to some indirection and mapping that is similar to physical memory, similar to the notion of virtual memory. So these three reasons are the reason why we do not have this picture, and we're going to modify it such that we go through a translation layer. CPU will generate virtual addresses, and we're going to map them to physical addresses. Okay. So basically, let me talk a little bit more about the difficulties of direct physical addressing in the picture that I showed. Programmer needs to manage physical memory space if you have direct physical addresses, meaning CPUs, loads, and store instructions directly reference physical memory locations. And this is clearly inconvenient and difficult, and it's bug prone also. And it's more difficult when you have multiple processes, because now you need to manage the physical memory space across multiple programs, which is even harder because they may be programmed by different programmers. So it's virtually impossible, basically, at this point. It's difficult to support code and data relocation because addresses are directly specified in the program. You basically say physical address 5. But what if that physical address 5 is also referenced by some other program, for example? Or what if you want to relocate it for whatever reason, right? And it's not easy to do this, basically, if you have direct physical address. As I said, difficult to support multiple processes. You do not have protection and isolation between multiple processes because everybody has the same physical address space if you have direct physical addressing. And as a result, you cannot distinguish between them. So you need to have some sort of protection and isolation mechanisms. And virtual memory provides one way of providing protection and isolation. There are other ways like segmentation, which we're not going to talk about. But essentially, segmentation essentially provides different physical addresses to different processes. That's it. It becomes difficult to share code if you have segmentation. You need to have different sort of segments, but it's actually used today in some systems, but as a legacy. For example, x86 64 architecture has segmentation in it still, so that it can separate processes in an early, very primitive form of protection and isolation. Processes have different segments, for example, so that they're isolated in physical memory. But virtual memory actually supersedes the protection and isolation that's provided by segmentation. So that's why we're not going to discuss segmentation, but you may hear the term segmentation. But it's essentially a way of isolation between different processes and different pieces of code in general. So, but segmentation makes it a bit harder to share physical memory space without problems. Basically, multiple processes sometimes want to share the same physical data. For example, you may have shared libraries. You may have shared code that's executed by different programs. In that case, you don't want to replicate things. In fact, it causes coherence problems probably if you replicate things. You would directly want to share code and data. And an additional level of indirection actually helps. Direct physical addressing doesn't help this. And then I think this is actually similar to this last point. Difficult to support data and code sharing across processes if you have direct physical addresses. Different processes need to reference the same physical address in some way, and it's not easy to do because they have to somehow coordinate different physical addresses. And how do you do that, right? How does programmer A know to use the same physical address as programmer B? You need to have a central database, and that becomes very, very cumbersome to maintain. Okay, so there are a lot of difficulties, basically. So that's why virtual memory was developed. And the idea is very simple. It has multiple benefits. But the main benefit, the idea is to give each program the illusion of a large address space. Oh, sorry about that. A large address space while having a small physical memory. Infinite memory, I would say. Let's say that's the illusion. So that the programmer does not worry about managing physical memory within a process or across processes. And that gets rid of all of the downsides that we discussed in direct physical addressing. Now, a programmer can assume they have an infinite amount of physical memory. Now, clearly, it's not infinite, but for all practical purposes, hopefully infinite. Hardware and software cooperatively and automatically manage the physical memory space to provide the illusion, essentially. And the illusion is maintained separately for each independent process. Each independent process has its own mapping. So the basic mechanism is indirection, essentially. Basically, as opposed to having direct physical addresses, we're going to have indirection and addressing main memory. So the address generated by each instruction in a program is a virtual address. So it's not going to be a direct physical address. In other words, it's not the physical address used to address main memory. This is also called the linear address in x86, basically. Virtual address is the linear address in x86. You will see some pictures of it later on. And then we will have an address translation mechanism that maps this virtual address to a physical address. So it's going to be indirection. It's going to be additional latency, and we're going to try to solve those latency problems. And this physical address is called a real address in x86, as we will see also. And this address translation mechanism is implemented in hardware and software together, as we will see. Okay, so this is from the chapter that I recommended that you read. Essentially, the conceptual view is that you have illusion of large separate address space per process. And this is a picture from the handbook. Essentially, you divide the virtual address space of each process into chunks. In this case, 4 kilobyte chunks. 4 kilobyte happen to be a good granularity that people use to do this mapping. And you can see that your virtual address space can be huge. In this case, 48 bits, 256 terabytes in a byte addressable system. And each process has its own virtual address space that's completely separate. But then there's a mapping mechanism that takes each process's virtual address space and maps it to the real physical address space on the system, which can be 8 gigabytes in this case. And you can see that there's a mapping mechanism that needs to happen so that you can actually have your data in physical memory when you actually really need to access it. So basically, this requires indirection between virtual and physical, and a mapping mechanism between virtual and physical spaces. So there are two ideas, indirection and mapping. Indirection requires the mapping, of course. And this is the view that we get now. This is a system with virtual memory. It's a page-based virtual memory. Basically, virtual memory is divided into chunks that are called pages. And in this case, it's 4 kilobyte chunks. Today's systems can be divided into multiple different granularities, as we will discuss. But 4 kilobytes is a good assumption for now. And basically, CPU generates virtual addresses. And there's a mapping table called page table, as we will see more of soon. The hardware and software cooperatively actually converts virtual addresses into physical addresses via an OS managed lookup table. So this lookup table called page table is managed by the OS, but it's accelerated by the hardware. Hardware looks up the page table and then converts the virtual address to a physical address. And this way you can enable multiple things. You can basically do the mapping, but you can also say, oh, this virtual address that I'm addressing right now is not in physical memory, so let me bring it from physical memory. So it may be actually in disk. So if it's not mapped in physical memory, it's probably in disk, or that needs to be indicated, of course. And then you can map it. Basically, the operating system and hardware cooperatively can bring it from the disk into the main memory, physical memory. This is called a page fault, and we will discuss page faults in this lecture also. Okay, so this way, programmer doesn't need to manage physical memory. from the programmer's perspective, everything is virtual. And the system makes sure that the data that's referenced by the program is brought from the disk into the physical memory before it's being operated on. And if physical memory is small, that's fine. The system basically manages the data and the mappings such that it brings the data that is really needed by the programs at this point and keeps it in the physical memory, and everything else goes back to disk. So now we're having a multi-level memory hierarchy, very similar to the caching system, as we discussed, managed by the operating system, as well as the hardware, as we will see concurrently. But the operating system actually plays a huge role here. But you do need the hardware to transfer the data as well, as you can see. But basically, this physical memory over here is a cache for the disk from the programmer's perspective in this case. And whenever you need the data, the automatically managed demand paging system brings the data into the physical memory from the disk. Okay, so hopefully that's clear. There are many issues over here that we will discuss in a little bit. But this is a page-based virtual to physical mapping. You can see each process may have a 4 GB virtual memory system. This is actually a simple example. But today, actually, we have 256 terabyte type of virtual memory, even larger, actually, depending on your address bits. It could be 64, but x86 uses 48, I think. They may have extended recently again. Who knows? But basically, you have two processes in this example. Physical memory is 16 megabytes, small. We divide the process into pages. We divide the physical memory also pages. I'm also going to call them frames later on. And you have virtual pages from the process perspective and physical pages or physical frames from the main memory's perspective. And then there's a mapping between done through the page tables. And page table is the lookup table to understand that mapping and also manage the mapping and also manage the hierarchy between the physical memory as well as the disk. Okay, so we're going to look at multiple issues here. There are at least 4 issues, at least 4 major issues, let's say, in indirection mapping. One question is when to map a virtual address to a physical address. I'm not going to delve a lot into this, but basically, when the virtual address is first referenced by the program, makes sense. Basically, it's demand paging. But of course, you can do prefetching as well. You can apply the same principles of prefetching that we discussed from the disk into the physical memory and change the mappings. Obviously, you can do that, but we're not going to talk about that as much. Modern systems do both. They do demand-based mapping as well as prefetching across the memory hierarchy, across the disk and physical memory. What is the mapping granularity? That's important because this determines the page table size. Is it every single byte? Is it kilobytes? Is it megabytes? Is it gigabytes? Is it multiple granularities? We will see that existing systems use multiple granularities because if the programmer knows how to map, that's great. If you can exploit the spatial locality in mapping, then you can reduce the page table size, right? But if you cannot exploit the spatial locality in mapping, if you map 1 gigabyte chunks, then there's a problem, right? If you access only 8 bytes within 1 gigabytes, that doesn't sound good, right? You need to bring in all of that data into the physical memory, or at least you need to have the space in physical memory for all of that data that's at the mapping granularity. Then where and how to store the virtual to physical address mappings? This is important. Page table clearly is one example, but how do you actually do it? Operating system data structures. Do you also store it in hardware? Do you cache it in hardware? And we will see that the answer is yes. Do you do it cooperatively between hardware and the software? And we will see that the answer is yes. And then the next question is what to do when the physical address space is full. Now you may know the answer to this. Basically, evict an unlikely to be needed virtual address from the physical memory. And this makes sense because physical memory is a cache for the disk from this perspective, right? Basically, you can manage physical memory similar to the principles that we have seen for cache principles. Okay, so let me introduce some more terminology. Virtual address space is divided into pages so that we can manage the large translation table sizes. You can map every single byte to another byte, but this doesn't exploit the locality in translations. And also, this doesn't make your translation table small. That's why we need to have large enough pages. And 4 kilobytes is a good size to start with, but people are actually increasing the size of these pages. Physical address space is divided into equally sized pages. These can be called frames. We're going to call them pages also in this case. You can call them both. A virtual page is mapped to a physical frame in the page table if the page is in the physical memory, or it's mapped to a location in disk otherwise, right? If it's not inside the physical memory. If physical memory is not allocated, if the virtual page is not referenced and the physical memory is not allocated, then it's in disk. If an accessed virtual page is not in memory but on disk, the virtual memory system brings the page into a physical frame and adjusts the mapping. This is called demand paging. You may have heard of this clearly. And page table is the table that stores the mapping of virtual pages to physical frames. Essentially, that stores the translations between virtual pages to physical pages, let's say. So essentially, in other words, physical memory as a cache is a cache for pages stored in disk, right? In fact, it is a fully associative cache in modern systems. A virtual page can potentially be mapped to any physical frame, as we will see in a little bit. And similar caching issues exist, as we have covered in caching. That's why we covered caching earlier than virtual memory. But basically, you need to do the placement, meaning where and how to place or find a page in physical memory. You need to do the replacement, what page to remove to make room in physical memory. You need to decide the granularity of management. What's the size of the page? Large, small, uniform. Now, since there's software management involved here, we actually have multiple granularities in existing systems, which we did not have in a level of cache. We need to take care of the write policy again. What do we do about writes? When we modify a page in physical memory, do we write it into the disk every time as well? Bad idea, because disk is so slow, right? So usually physical memory is a write back cache for the disk, right? That's why you need to keep track of modified blocks or modified pages in physical memory as well. So physical memory is no different than a cache, essentially. In fact, you can do this analogy. Cache block is a virtual memory page. Cache block size is the virtual memory page size. Cache block offset is the virtual memory page offset, as we will see. A cache miss is a page fault in virtual memory. Cache index and tag bits are decided by the virtual page number in virtual memory, as we will see. Okay, so page size is the mapping granularity of virtual to physical address spaces. We will see different page sizes soon. This also dictates the amount of data transferred from hard disk to DRAM at once, or amount of data that needs to be allocated in physical memory. That's why having a large page size is dangerous, because you may need to transfer a lot of data, even though you may not be using it. This is very similar to a cache block, right? We said the same thing for cache blocks. This determines the page table size. Page table is essentially the tag store, right, for the cache. I mean, I didn't say this explicitly over here, but we can add page table as potentially a tag store for the physical memory. Page table is a table that stores virtual to physical page mappings. It's really a lookup table used to translate virtual page addresses to physical frame addresses, and where to find where the associated data is. So this is essentially, you can think of the translation table or a tag table as well, from the cache terminology, of course. And then address translation is the process of determining the physical address from the virtual address. So let's go over some examples of this. So basically, remember this, I showed you this picture in the memory hierarchy. I said we want to build a memory hierarchy because with good locality of reference, memory appears as fast as this cache, but as large as this larger entity, main memory, for example. And the same thing applies for cache and disk, or physical memory and disk as well. Basically, the goal is to be as fast as this physical memory while getting the large capacity, infinite capacity from the programmer perspective as a disk. And hopefully most access is hidden in physical memory, and programs see the large capacity of virtual memory. And this is the example address translation. Basically, you have a virtual to physical address mapping that's determined by the page table. And this is how you do the translation, basically. So let's assume that this is from your book also, so you can read your book for more details and detailed explanations. But they basically look at a 31-bit address space. It's 2 gigabytes, and a 27-bit physical memory space. I think it's 128 kilobytes or megabytes, sorry. And basically, the translation happens at the page granularity. So at the bottom parts of the bit, page offset, this is very similar to the byte in block in caches, for example. It's 12 bits. That's 4 kilobytes, right? So page offset doesn't get translated during the translation process, but virtual page number gets translated into a physical page number or physical frame number. And that translation is done by the page table, essentially. So let's take a look at an example of a virtual memory system. So a virtual memory size is 2 gigabytes. I showed you earlier, actually. You have 31 bytes. Physical memory size is 227 bytes. Page size 4 kilobytes, 212 bytes. Many systems have 4 kilobyte pages today. Some of them are 8 kilobyte pages. Organization looks like this. Virtual address should be 31 bits. Physical address should be 27. Page offset should be 12 bits. Now you can compute the number of virtual pages in virtual memory. It's 2 to the 19, as you can see. So virtual page number should be 19 bits. And physical pages in physical memory, which is 2 to the 15, by dividing the physical memory size with the page size. And physical page number is 15 bits. So these are very easy things. And this is the mapping table, basically shown in your book also. Basically, we don't explicitly show the page table. We're going to see that in a little bit. But essentially, virtual addresses are mapped at a page granularity. That's why you look at virtual page number to physical addresses. And you have the physical frame number, right? So offsets don't change, page offsets don't change during translation, but the virtual to physical translation in terms of page numbers happen. So you can see that some of them are in physical memory. The blue ones are in physical memory. The non-blue ones are not in physical memory, and they're mapped to disk. Okay, so how do we translate addresses? Page table has entry for each virtual page number, essentially. It has to. Otherwise, you cannot translate an address, and otherwise you won't be able to support virtual memory. Each page level entry has a valid bit, very similar to a cache again. And this basically specifies whether the virtual page is located in physical memory, whether the virtual page is cached in the physical memory, essentially. If not, it must. If you get an invalid bit, if the page table entry that you're accessing is invalid, you need to fetch it from the hard disk. Basically, that's a page fault. Then you need to have the physical page number inside the page table entry. This basically specifies where the virtual page is located in physical memory. And also other bits like replacement policy bits, dirty and modified bits, like in caches. And we also will talk about protection, access control in the next lecture. So you need to have permission and access bits in many page table entries. So this looks very much like a cache, as you can see. Valid bits and a tag, if you will, right? Okay, so let's take a look at the page table for our example earlier. This is the page table, basically. For each virtual page, you have an entry that has a valid bit. In this simple case, it just has a valid bit and the mapped physical page number if the page is in virtual memory. If the valid bit is 1, you'd better have the correct mapping. If the valid bit is 0, then that means it's in the disk, right? So let's take a look at some example translations quickly, and then we're going to conclude and go for the next lecture. Essentially, going over here, and these are examples from your book also, so you can follow from your book if you need to go somewhere at this point. But basically, this is how a virtual address is translated. Virtual address is 31 bits, as I said. The bottom 12 bits is offset. We need to access the page table for that virtual page number. So a page table is stored in physical memory, and this is going to be an issue later on that we're going to solve. But page table has a page table base register, and each page table entry, as I said, stores each virtual page number corresponding valid bit and physical page number. If valid, physical page number specifies the valid map location in physical memory. Otherwise, it says it's in disk, and it may contain information on how to fetch it from the disk, for example. But page table is located at physical memory. We're going to question that later on. But it's at a physical memory address specified by the page table base register. This is part of the context of a process. So each process has its own page table base register. Whenever you do a context switch, you need to modify the page table base register so that you reference the correct page table, right? Because each process has its own view of virtual memory, right? And the translations. Okay. So you basically index the page table using the virtual address that the program has generated. In this case, virtual page number is 2. So basically page table base register plus the 2. So we basically index the second entry of the page table. And it happens to map to this location. It happens to be valid, as you can see. Page table provides a valid bit and the PPN, physical page number. If it's valid, then you get the physical page number and append it to the page offset, and that's your physical address. So that's how you do the translation. If the page table entry at the virtual page number coming from the virtual address is valid, you basically replace the virtual page number with the physical page number that's inside the page table entry, and that's your physical address concatenated with the page offset. And now you can access your cache hierarchy. Okay, sounds perfect, right? So page offset bits do not change during translation, as I showed you earlier clearly. Okay, so let's do some examples. I mean, you can do this on your own also, but and also there in the in your book as well. But basically, the question is, what is the physical address of virtual address 0x5f20? And by now, you know, we have the assumption that last 12 bits are the page offset, top 19 bits are the virtual page number. The first step is, how do you determine the virtual page number? You first need to determine the virtual page number, and based on that, find the page table entry containing the translation for the corresponding VPN. And the hardware needs to do that in the processor. So hardware needs to look up the page table entry at the address corresponding to the virtual page number in the page table of this process. And how does the hardware calculate that address? It basically takes the page table base register, which gives you the base address of the page table. It adds to it virtual page number times the size of a PTE, page table entry. And that's the memory location, memory address of the page table entry that houses the translation for the virtual address that has that virtual page number, right? That's the idea basically. And the hardware needs to generate a memory access to do the translation, as you can see. So there's going to be overhead for us because remember, we said indirection. Indirection means another memory access to do the translation. So we need to access the page table, which is in physical memory, to get the translation for a virtual address so that we can access the memory at the physical address corresponding to that virtual address. That's the idea over here. So this is the address that you need to access in physical memory to get the translation. Page table base register plus virtual page number times the size of a PTE. Okay. Size of a PTE can be 4 bytes, 8 bytes, depending on the implementation. Clearly, this needs to be specified in the ISA also. So in this case, virtual address, it looks like this, 5F20. So bottom 12 bits are page offset. The top 19 bits correspond to virtual page number 5. So we need to index virtual page number 5, get the entry 5 in page table. And if you look at entry 5, if you do the memory access, page table base register times 5 times the size of a PTE, page table entry. It could be 4 bytes or 8 bytes, whatever. It doesn't matter. You do the memory access here. You get this page table entry. It's valid. That's great. And it has a physical page number. Now you can actually say, oh, this is in physical memory. And the physical address is 0001 F20. That sounds good, right? I mean, this is, I just spent more time explaining it so that you're more comfortable with it, but you can read the paper also. You can read the book also. So there's one question very quickly. Do caches also use virtual memory? We're going to get back to it. We're going to get to it tomorrow, not today. But so far, assume that caches use physical memory. But L1 caches are special, and we may actually want to do something special with them because we may not wait. We may not want to wait until the address translation happens, but patience, we're going to get to it. Okay, let's take a look at another example in this particular page table again. What is the physical address of this virtual address? 0xF73E0. We do the same thing basically. Chop up the virtual address into page offset and virtual page number. Ignore the page offset for now. That's not going to change during the translation. Virtual page number now we know is 7. So if you look up entry 7 in the page table, the processor does this by accessing memory, and it finds out page table entry has a val bit of 0, which means that the page, the virtual page that we're looking for is not mapped into physical memory. So the virtual, and this is called a page fault. So the virtual page must be swapped into physical memory from disk. And now the system needs to take some action so that it brings the virtual page from disk into physical memory. It adjusts the mapping afterwards to 1 and then changes the physical page number over here, and then does the translation again at that point. And then you can get the translation. So at this point, just by accessing the page table, you cannot do anything because virtual address is not mapped to physical memory. So the answer is you don't know the physical address, basically. It's a page fault. So we're going to cover some issues, but just to prime you for what's coming next in the next lecture is page table size is problematic. So assume a 64-bit address space over here. You can see page offset, assume 4 kilobyte pages in this case. So your virtual page number is 52 bits. And assume that your physical address is 40 bits. So you need 28 bits physical page numbers and 12-bit page offset. So page table does a 52-bit to a 28-bit mapping, basically. 52-bit virtual pages are mapped to 28-bit physical pages. How large is the page table? Well, I didn't give you everything over here, but you definitely need to have 2 to the 52 entries. Assume that each page table entry is 4 bytes, which is a stretch, because it's going to be actually bigger than 4 bytes because you need to store some other information than just the physical page number and the valid bit. So 2 to the 54 bytes. That's a lot of memory, right? And that's just for one process. You don't want this to be in physical memory because your physical memory, this is larger than your physical memory, right? We just said that your physical memory is 40 bits, 2 to the 40 entries. You cannot store a 2 to the 54 byte page table in it. This doesn't make sense. And this is just for one process. What if you have hundreds of processes? Now it's impossible to have actually the entire page table in physical memory. And we're going to tackle this issue tomorrow. And also, the process may not be using the entire virtual memory address space as well. This is going to be important and interesting as we talk tomorrow. But I think this is a great place to stop because now we've come to interesting challenges because we learned the basics of virtual memory, which you can also read in your book. But tomorrow we're going to tackle some challenges like page table is large and page table translation is slow, and we're going to solve those challenges. And hopefully we're going to go into even more interesting challenges. So I'm going to stop here today. If there are any burning questions, I'm certainly happy to take them. I think there were a lot of good questions that were asked in this lecture, so it's fine if we don't have any questions. Tomorrow is going to be our last lecture, and we're going to finish up virtual memory, and we're going to have an epilogue. And feel free to prepare questions for tomorrow also. So hopefully we'll have an interesting last session talking about exciting topics. So until then, have a good evening, and I will see you tomorrow.